Hello, chemistry students. It's Mr. Duffy. Welcome to our first lesson in Unit 2, which is about the atomic theory. Now, today's video, there's not a picture of me. I'm making this video at home, and I don't have a webcam, so hopefully you don't mind that my picture isn't in the bottom right. Let's go ahead and get started. In this unit, we're going to be talking about four main concepts, four guiding questions. How do we know atoms exist? That's what we're going to try and cover in today's lesson. How do we know that atoms are made of electrons, protons, and neutrons? That'll be covered in a later lesson. And then are all atoms in an element the same, or are there differences between them? And then again, last question is what makes some atoms stable and what other atoms aren't? These are all the, again, guiding questions that we'll cover throughout this whole unit, which will take us about 4 weeks to cover. So let's talk about the development of the atom, the concept of the atom. To understand that, we have to go back to ancient Greece, and we're going to talk about the elements that they thought existed were the elements of fire, water, earth, and air. Ancient Greece is again the start of our story. It's the history of the atom, but um, there's no evidence for the atom back in ancient Greece. They really talked about what the idea of an atom might be, what matter is actually kind of composed of. And again, they came up with those four elements: earth, wind, fire, and air that we carried actually through us to about the 1600s. These concepts from ancient Greece. The first person we want to talk about when we go back to ancient Greece is Democritus. Democritus is a very important philosopher during this time period, and he comes up with the idea of democracy, but that's not what we're going to be talking about in chemistry. His idea of the atom, or atomos, is what we want to be talking about in chemistry. Basically, he said that matter is composed of individual atoms, which cannot be divided, and we came up with the term atom from him actually. So he's the person that kind of created this word that we now carry on today. Um, he had no experiments to actually support that atoms actually existed, and there were others philosophers of this time that kind of thought matter continued on forever. There was no small unit of matter. There was no atom, and so he kind of had to compete with these other individuals to explain that his idea of what an atom was. But basically, his idea of an atom was basically a three-dimensional sphere. Um, Small, tiny particles could not be destructed. It was a solid particle. He did not know anything about protons, electrons, or neutrons. He just said, again, this was the smallest particle that you could have of matter, and there could be different types of atoms and so forth, but um, all matter was broken down into these small individual particles. Now, other philosophers also kind of thought this as well, that there were small atoms, but they thought there were only four individual atoms, four individual elements. And that's where the earth, water, fire, and air kind of come into play. These were Greek philosophers, Aristotle and Plato. Um, they thought all matter, everything that was around them, was composed of these four basic elements in different combinations. So if you go back to that comic strip that I showed you on the first slide, um, a clay pot has 40% earth and 20% water, 11% fire, and 29% air. That's the joke behind it. But again, that's what they thought, that there were four basic elements, and different proportions of these elements made the different materials. And since these Greek philosophers were not scientists, they didn't do any experiments. It was actually beneath them to do experiments. There was no proving who was right. They just had to settle their arguments based on by arguing with each other, debating each other. And Aristotle won the debate over Democritus during this time period because he was more famous. He was a better philosopher. And so we carry on the four basic elements as opposed to kind of individual atoms, because he won those arguments. And since he thought that all atoms, all these elements, all materials were made of these four basic elements, people thought you could change the proportion. And so his ideas carried on through the Middle Ages, where alchemists were trying to change different materials into gold by changing the proportion of those four different elements. And so that leads us again, basically up through the Middle Ages with chemistry called alchemy, a science called alchemy, if you want to call it a science. But basically, people were trying to understand the world around them, understand matter, by trying to change cheap materials into expensive materials like gold. And a lot of old Middle Age movies and stuff talk about alchemy as kind of like a magician, and that's actually kind of what some of them were. They were made elixirs for physical immortality and potions and things like that. Um, so again, not necessarily 100% science and during this time period, but they did make some contributions to science. They found out information about certain elements, certain things. They found certain elements were discovered during this time period. Some of the properties of the elements. They developed different lab materials like test tubes and beakers and so forth. Some procedures that would be carried on throughout history. Some techniques. Learned how to make acids and bases, and developed several different alloys of metals that were, stronger. New glassware. But again, that's kind of where their contribution kind of ends, because it's not alchemy was not real science. So it takes us into again the end of the 1600s, late 1700s, before people start doing more actual science, and we come to a guy named John Dalton. He was an English school teacher, and he summarized the results of other scientists during the time period again that were actually doing experiments and could back up their results with evidence. And so he didn't actually do any of the experiments himself. He summarized the experiments of others into an atomic theory. And here's his atomic theory. It's kind of four main parts. Um, he said all material is made up of tiny particles called atoms. All atoms of the same element are identical. A chemical compound has ratios of atoms, the same ratios of atoms. And in chemical reactions, atoms from one or more elements or compounds rearrange to form new compounds. The atoms do not themselves change their identity. So, kind of these four basic concepts, these four main concepts in his atomic theory, were all founded in other scientists' experiments. So that's where we're going to kind of be talking about these foundation for his atomic theory. The first foundation for his atomic theory was the law of conservation of mass. It basically says that mass cannot be created or destroyed during a chemical reaction. Second foundation was the law of definite proportions. It basically says that a chemical compound contains the same elements in exactly the same proportion of mass, regardless of the size of the sample. So again, we'll go into it in more detail in a later slide, but the final basis of his atomic theory was the law of multiple proportions. And it says if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with the certain mass of the first is always simple small whole number ratios. So let's talk about each one of these foundations a little bit more in detail, starting with the law of conservation of mass, conservation of atoms. The law of conservation of mass basically says that what you start with has to be what you end with. So if we have a reaction between hydrogen and oxygen, we can kind of see that we start off with 4 atoms of hydrogen, 2 atoms of oxygen, and after they recombine and change into water, there are still, though, 4 atoms of hydrogen and 2 atoms of oxygen. Nothing has changed, no atoms were gained, no atoms were lost, they were just rearranged. And this is, again, a basic principle that John Dalton put into his atomic theory, but he did not do this experiment himself. What we can kind of think of is that in this concept, the law of conservation of matter is kind of like a Lego. We can take different Legos, I can take them apart and put them in different places, but if I start off with five Legos at the beginning, and if I rearrange them into different pieces, I still have 5 Legos when I'm all done. And that's kind of the basis of what atoms are. They can be rearranged into different substances. Now, another law that John Dalton used in his atomic theory was the law of definite proportions. And basically, this law says that each compound is a specific ratio of the elements. It's a ratio by mass, weighing before and weighing after. But water, for example, is always 8 grams of oxygen for every 1 gram of hydrogen. It's always going to be that way, no matter where I get the water from. If I take it out of a lake or stream or get it out of a drinking fountain, water is always going to be 8 grams of oxygen in it for every 1 gram of hydrogen. And so Joseph Proust was the guy that came up with this. But basically, again, he took different combinations, different proportions of different substances, and he always got the same amounts. For example, here in this slide, we can look at he combined lead and sulfur and makes a compound called lead sulfide. If you took 10 grams of lead and 1.56 grams of sulfur, he always got 11.56 grams of lead sulfide. This was kind of like the perfect ratio for him. But he tried and experimented with different proportions. He took three 10 grams of lead and 3 grams of sulfur, and he combined it together. He found that it didn't make more lead sulfide. It still made exactly the same amount of lead sulfide, and he just had leftover sulfur. Well, he's tried with more lead. So more lead, 1.56 grams of sulfur combined. Tried to figure out again what's going on here. It actually made the same amount of lead sulfide, and he had leftover lead. So basically, what he was finding out here was that elements combine in certain ratios, and if you change those, they don't just make more. You end up with some leftover materials. So again, they only combine in certain ratios by mass, and that was the law of definite proportions. No matter how much he started with, he still ended up with a definite proportion at the end. The law of multiple proportions is a little bit harder to understand, but basically, he had to use this law of multiple proportions because there was no reliable scale for atomic mass units during this time frame. It was only a scale based on like grams. So based on that, he had to come up with what was called a general statement known as the law of multiple proportion. And actually, sorry, John Dalton did come up with this statement. So this law states that when two elements form a series of compounds, the ratios are basically simple whole number ratios. Here's an example of this. If I take water and I take hydrogen peroxide, they're both made out of hydrogen and oxygen, but hydrogen peroxide basically has 2 oxygens. If we compare the ratio of oxygens between water and hydrogen peroxide, it's always going to come out in a 1-to-2 ratio. Now, why does this make sense? Why is this happening? Basically, it's saying that um, it's always going to come out as, again, a whole number ratio because you always have to add a whole nother atom to the other compound. So again, if water is 8 grams oxygen per 1 gram of hydrogen, hydrogen peroxide, which is H2O2, is going to be 16 grams of oxygen per 1 gram of hydrogen because it is a 2-to-1 ratio because I'm adding a whole nother atom to the mix. I can't add a portion of an oxygen atom. I have to add a whole nother atom. They come in whole numbers. You can't add fractions. No fractions. And so with those 3 foundations for his atomic theory, again, he basically, again, I'm just going to restate his atomic theory after going through and combining all the scientists' work. He stated that elements consist of tiny particles called atoms, and that elements are pure substances because atoms are making up elements, and he said they were identical, had the same mass, and so forth. So, again, statement number 1 is all material, Dalton said, like the ancient Greeks, all material is made up of atoms, these small tiny particles. They cannot be subdivided or changed, or there's no smaller portion other than the atom. Nothing's smaller than an atom. They can't be created or destroyed. That's based on the law of conservation of mass. All atoms are identical in mass, size, and other properties. All atoms of one element are different in masses and properties from other elements. And in chemical reactions, elements combine in simple whole number ratios. They have to be whole number ratios. Now, this was again the basis of the atomic theory, the first atomic theory based on evidence. And that's why this is so significant. Um, it We could give credit to Democritus coming up with the idea of an atom, but he had no evidence for an atom. Dalton actually has evidence. And so this is, again, a significant breakthrough in chemistry. Now, we know that Dalton was not 100% correct. And so that's where we're going to go in future lessons, talking about, again, some issues with Dalton's theory. But it was improved upon. We know that now that all atoms do not have exactly the same masses. There are nuclear reactions. There are things that are smaller than atoms, like the protons, the neutrons, and electrons. But it was a starting point, and so again, that's why Dalton's atomic theory is important. So, hopefully, after watching this video, you are able to answer the question: how do we know atoms exist? And through the concepts of Dalton's experiments, Dalton's summarizing other scientists' experiments, you can realize again that atoms do exist. So, thank you for watching.